Welcome to the third knowledge clip of physical chemistry of the life sciences for the section thermodynamics. The last time we spoke about the Gibbs free energy, and we learned that the Gibbs free energy is a measure of the maximum amount of non-volume work that a system can perform. Furthermore, we learned that the Gibbs free energy or the change of the Gibbs free energy is an indicator for whether a process or a reaction occurs spontaneously. In this knowledge clip, I want to show you how the Gibbs free energy also shows us whether a system is at equilibrium or not. And also I want to show you how the Gibbs free energy depends on both the pressure and the temperature. So let's get started. So as we discussed in the last class, the Gibbs free energy decreases for any spontaneous process. What do I mean with a spontaneous process? An example is when you add a few droplets of a dye into a beaker filled with a liquid, with a solvent. Over time, the dye will mix with the solvent and uniformly distribute within that beaker. That's spontaneous. That will always happen. It will not go the other way around, so that all the dye molecules will concentrate again into a droplet. That's not spontaneous, but the distribution of the dye is spontaneous. Another example of a spontaneous process would be the freezing of ice below 0 degrees Celsius. We all know that when you have liquid water and it's exposed to temperatures of say -5 degrees Celsius, it will turn into solid ice. That's a spontaneous process. Maybe if you have two blocks of metal, one is hotter than the other, and you bring them together, over time, both blocks will reach the same temperature. That's also a spontaneous process. I could continue with countless examples of spontaneous processes, and I'm sure you could as well. But generally, for all of these, the Gibbs free energy will decrease. So the definition of the Gibbs free energy, G, is the enthalpy H minus the temperature times the entropy. So the Gibbs free energy is an extensive property of the system. That means it depends on the amount of molecules which are in the system. It depends on the mass of the system. Why is that? Just because the enthalpy as well as the entropy themselves are extensive properties. So the Gibbs free energy is made of two extensive variables and therefore is itself an extensive property. So if we want to calculate a change of the Gibbs free energy, we can do this as follows. We take an infinitesimal small change of G, and then we just take an infinitesimal small change of H and subtract minus dTs. And that gives us minus TdS minus STT. We once again have applied the product rule here. So if we look at a Gibbs free energy change at a constant temperature and pressure, first, let's take a look at constant temperature. That means this term here, dt, will cancel out since T is constant and dt is 0. So all that will be left is going to be dH minus TdS. The other parameter, the pressure, if we consider this to be constant, then we were able to relate this expression to the entropy change of the universe, the second law of thermodynamics, because considering a constant pressure allowed us to replace the heat that crosses the system's boundary with the enthalpy change. And that's how we could express the entropy change of the reservoir that surrounds the system with the enthalpy change of the system. So you see this in the last lecture. And this way, we were able to connect the free energy change, the Gibbs free energy change, to the entropy change of the universe, minus TdS universe. And the second law of thermodynamics tells us that the entropy for a spontaneous process always increases, but the negative temperature times the entropy change of the universe, therefore, must then always decrease, right? And that's the important criterion that the Gibbs free energy has. It always decreases for a spontaneous process. Okay, so I'm plotting here now the Gibbs free energy on the y-axis and a process variable x which is characterizing the progress of the reaction. Could be the time, it could be the temperature of the system. I plot that as the x-axis. And I will draw a graph of the dependency of the Gibbs free energy on x at constant pressure and temperature. And it will typically look like this, like a U-curved shape. And now at any point of this U that is not at the bottom, we can state that this is a non-equilibrium point. Why is that? Because if we take a closer look, the curve at that point, if we are going up, then the Gibbs free energy will always increase. So that is not what a spontaneous process would do, and therefore it would actually go down instead towards a negative change of dg. So this basically, the direction is indicated by into which direction dg will be negative. So in this case it will go down for a decrease of g towards for a spontaneous process. At the bottom, on the other hand, of this graph, here we are at equilibrium. Why is that? Because at that position the curve that describes the Gibbs free energy is horizontal basically, and we can measure the derivative of the Gibbs free energy, meaning how does it change with this process variable. At that position it will be 0, it does not change anymore, and therefore we can state at equilibrium the Gibbs free energy does not change with respect to that process variable x, which can be the temperature, the time, the pressure, or the entropy or internal energy of the system. So once the Gibbs free energy has decreased during such a spontaneous process, it will reach an equilibrium state at which the Gibbs free energy does not change anymore. Okay, so in this second part of this knowledge clip, I would like to discuss with you how does the Gibbs free energy change with the pressure and the temperature, right? And before we answer this question, first I'll introduce a different way of writing the Gibbs free energy. Here I write G bar. What does that bar mean? It means that this is the Gibbs free energy per mole of the substance that the Gibbs free energy describes here. So the unit is joules per mole. So whenever I write this bar above an extensive variable, such as the internal energy, the volume, or the entropy, then that means it's always per mole of the substance that this extensive variable describes. Right? Okay, back to our question. How does the Gibbs free energy depend on the pressure? Now I express this here as g of p, yeah? Just like, you know, a function y of x. Yeah? So I write this here. And in order to find out that pressure dependence, what we need to know is first, what is the value of the Gibbs free energy at a specific reference pressure, P naught, right? We need to know that, and with that knowledge, we can then add an so-called extrapolation, which is given by this integral. It may look a little scary to you at first, but actually it's quite simple. You'll find out on this slide. So what is the integral doing? It is integrating from the pressure P naught to the pressure P at which we want to know the value of the Gibbs free energy. And what does it integrate? It integrates this partial derivative of the Gibbs free energy. So you can see the partial derivative is written with these delta symbols rather than the D letters, which we conventionally use. And why the delta? Because the Gibbs free energy does not only depend on the pressure, it also depends on the temperature, right? So, but now here we want to look at how the Gibbs free energy changes only with the pressure, and that's why we use the partial derivative, and then we say that the other variable that the Gibbs free energy depends, the temperature, is constant, simply, right? And so you can actually see what the integral is doing here. You have here delta G over delta P times dP. And in principle, those delta P and dP, right, they cancel each other out each time. And then you only have delta G's. And then you basically, the integral, it adds all these little delta G's up and then adds it on top of this value of the G at the known reference pressure P naught, right? Okay, so again, this is what we want to calculate, the Gibbs free energy at a certain pressure P. But we need to know the value of the Gibbs free energy at a reference pressure. And we do this by so-called extrapolation. Okay, so in order to evaluate this integral here, we need to take a look at the thermodynamic quantities once again. So first we need to find out how does this partial derivative of the Gibbs free energy, how does it actually depend on the pressure? We need a formula for this partial derivative. We need an expression, and we can obtain that by taking a look at the enthalpy internal energy and how they connect to the Gibbs free energy. So we do that now first with the enthalpy. The enthalpy H, which I also write now as per mole with the bar, is given, as you know, by the internal energy plus the PV term. Everything per mole now, all the extensive ones, not the pressure, because that's not an extensive variable. So then we can calculate an infinitesimal small change of the enthalpy, and that's simply du plus dPV, and the product rule gives us PdV plus VdP, as we have seen before. Now the du can be expressed with the first law of thermodynamics. du is simply the heat that flows minus the volume work, PdV. And we do not consider non-volume work here, so only classical system. And then the remaining two terms, plus PdV and plus VdP. And now, excellent, we see that we can cancel out this minus PdV and this plus PdV. And with this, we just have TdS plus VdP. And I already replaced the dq now here with TdS, which is expressing the heat transfer with the entropy change of the system. And the VdP remains here from the definition of the enthalpy. Okay, so now back to the Gibbs free energy, G. And we know the formula for Gibbs free energy is enthalpy minus temperature times entropy. And now I can just replace, or I carry out again the infinitesimal small change of the Gibbs free energy, dG. So that means dH minus dTs. And the product rule gives us minus TdS minus SdT. And with this expression, we can plug in the definition of the enthalpy, which we have obtained here for the enthalpy change. And that gives us TdS plus VdP, and the two remaining terms minus TdS and minus SdT. And once again, I can cancel out some terms here, which would be here the TdS term and the minus TdS term. Excellent. So with this, the formula becomes simpler. dG is now simply VdP minus SdT. Excellent. Looks much simpler than it did before. Okay, now we have this expression for dG. And I can write this actually with partial derivatives. Instead of writing VdP, I can write the partial derivative of dG over dP at constant temperature here times dP. And instead of the entropy here, I can write the partial derivative of the Gibbs free energy with respect to the temperature at constant pressure times dt, right? This is now where we get our definitions of the partial derivatives. First, we know that the partial derivative of the Gibbs free energy with respect to the pressure is the volume. And second, we know now that the partial derivative of the Gibbs free energy with the temperature is given as the negative entropy. Excellent. So here we basically have now what we needed, which was an expression for how the partial derivative of the Gibbs free energy with respect to the temperature, which is obtained here from this analysis. And it corresponds to the molar volume, the volume per mole. Okay, and then we can rewrite this extrapolation to obtain the Gibbs free energy at a specific pressure simply by, again, the reference Gibbs free energy plus the specific volume now, or the molar volume, since we have now replaced the partial derivative here with this molar volume, times dp. Up. Okay. So we found out that the partial derivative of the Gibbs free energy with respect to the pressure simply corresponds to the molar volume. Good. Now the question is, how does the molar volume depend on the pressure? Right? For an ideal gas, our favorite example, we have a simple equation that relates pressure and volume via the moles, the gas constant, and the temperature. Excellent. We can actually rewrite it by dividing the volume on the left with the number of moles, and that is actually the molar volume, right? It's the cubic meters per moles. And the gas equation rearranged then is simply the RT on the right side divided by the pressure. Excellent. Here we have an expression for the molar volume and how it depends on the pressure. This is what we can plug in here now. So the Gibbs free energy of an ideal gas at a specific pressure is calculated by adding this extrapolation of the molar volume over the pressure from the reference pressure to the pressure where we want to know. And now we know the gas constant and the temperature, they are both constant, right? We said that the temperature is constant already in this definition, up here, that we want to see how the Gibbs free energy changes with the pressure at a constant pressure. So when these two are constant, they can be taken out of the integral, and we only need to integrate dp over p from the p naught to p. And that is a standard integral. It simply gives us ln p divided by p naught. Excellent. This is the expression that tells you how the Gibbs free energy of an ideal gas depends on the pressure. Nice. So if we want to look at solids and liquids, what is nice about those, they are considered incompressible at moderate pressures. That means they don't change their volume really significantly when the pressure changes. And with moderate, let's say, I mean something like 1 atmosphere to maybe 50 atmosphere. I'm not exactly sure about the upper bound, but pressures that are not very high. At very high pressures, also liquids and solids will become compressed, but pressures that for us are okay to survive, let's say, then liquids and solids, their density or their molar volume doesn't change. That means that the molar volume is a constant, simply. And with a constant in the integral here, we can evaluate the integral even more simple. So now we can simply write for solids and liquids the pressure dependence of the Gibbs free energy. Again, it's the Gibbs free energy of the reference pressure. But now just the constant molar volume can be taken out of the integral, and then we just integrate dp from p naught to p, and that's just p minus p naught. Very simple. So what that means for solids and liquids, when I plot the Gibbs free energy as a function of the pressure, it's just a straight line because the slope of the dependency is just the molar volume, basically, right? Nice. So this is how generally in thermodynamics you can obtain the value of certain state functions like the Gibbs free energy or the internal energy at different conditions via extrapolation. This is a general approach in thermodynamics, and it works very neatly. The same thing can be done basically for the temperature, right? The Gibbs free energy dependence on the temperature simply is the Gibbs free energy at a certain reference temperature, T0, plus this extrapolation of the Gibbs free energy as a temperature dependence. Great, thanks. This is actually the end of the third knowledge clip, and in the following knowledge clip we will talk about how Gibbs free energy changes for chemical reactions can be quantified. Good, thanks.